in the previous chapters and everything we've done so far in organic chemistry, we have focused primarily on the structural aspects of atoms, molecules, and ions. We asked a lot of questions about the nature of the chemical bond and about how electrons are distributed in a given molecular ion. And then we also looked at the similarities and differences among different types of isomers. Now in chapter 6, we're really going to start shifting our focus to chemical reactions and spend a lot more time, and really the rest of our time in organic chemistry, focused on those chemical reactions. So to be able to do this, we need to understand a few just basic pieces of information about chemical reactions, okay? And we're going to really start here with mechanisms. So when we talk about chemical reactions, this is no different than general chemistry, where we just define this as the transformation of one substance, which was a reactant, into another substance. Right? And it typically occurs through the changes in bonds. So bonds have to break and bonds have to form. But in lab, to us at least, this occurs as, or appears to occur a lot of times, as one smooth, continuous process. But if we could observe a reaction on the molecular level, we would see that the reaction occurs in distinct events called elementary steps, each of which is nearly instantaneous, and it changes the geometry, and it involves those breaking and forming of bonds. Now, that precise sequence of elementary steps that results in the conversion of the reactant into the product in this chemical reaction is called the mechanism of the reaction. So when we talk about the precise sequence of elementary steps that results in the conversion of a reactant into a product, that's called the mechanism of the reaction. So these are those elementary steps. Now we looked at this a little bit in general chemistry, but we're really going to settle down into mechanisms. Now mechanisms are really helpful for us. Mechanisms can be used to help us with a lot of things. They can illustrate how a reaction takes place. They can help us understand why a reaction takes place. Excuse me. I apologize. And then they can ultimately help us make predictions, right, about reactions that we haven't seen before. So for every new reaction in this book that we're going to talk about, we are going to focus on its mechanisms. And mechanisms really help us simplify organic chemistry, because most reactions are constructed from the same set of elementary steps. Now, we're going to begin with the proton transfer reaction, which is the topic of this entire chapter, because it's one of the simplest reactions that you're going to encounter in organic chemistry. It's also the most common elementary step found in organic reactions. And then in chapter 7, what you're going to see is we are going to look at a handful of other elementary steps. And but the concepts that we learn here can be applied to those other reaction mechanisms. So let's introduce kind of the main star of this chapter, which is our proton transfer reaction. Now, the proton transfer reaction is going to build off of something that you learned in general chemistry, which was the Bronsted-Lowry acid-base definition. And so when we define a proton transfer reaction, right, this would also be a Bronsted-Lowry acid-base reaction. And that's just one where a Bronsted-Lowry base reacts with a Bronsted-Lowry acid. Okay. I want you to remember that when we talk about Bronsted-Lowry acids and bases, the acid is going to donate the proton. So it's going to give up its proton. I want to remind you that protons are shown as H+. So they're not hydrogen atoms. Hydrogen atoms have one electron. This is protons. And then a base, a Bronsted-Lowry base, is going to accept a proton. So we can see here overall a proton transfer. So the proton here is shown in blue, and it is going to be transferred from the acid to the base. So this is hydrochloric acid. This is a hydroxide anion, which is an OH minus, and that gets transferred to the base. One of the things to be aware of, and this is just a brief reminder, is that the conjugate acid is the species that results after the base picks up a proton. Okay, so would be a conjugate acid-base pair. And then the conjugate base is the species that results after the acid loses the proton. So HCl has lost an acid, and it has formed a conjugate base here. This is an important definition. We will refer back to acid, base, conjugate acid, and conjugate base. So make sure you understand that. The proton transfer reaction just simply consists of a single elementary step in which the bonds break and form simultaneously. So when we talk about this, right, we say, hey, look, this is a single elementary step, right? And what's happening here, of all the changes that occur in the reaction on this molecular level, they do it simultaneously, so they're said to be concerted, right? So all the bonds break and form simultaneously. So it's all happening at the same time. And so the reaction is said to be concerted. And that's a kind of a new vocabulary word for us. And you'll see that used again and again throughout the rest of the course. So organic chemists follow these changes that happen in these reactions by keeping track of the arrangement of valence electrons. So when we look here at this equation, right, we see a single bond is broken between the chlorine and the hydrogen, and then a single bond here is formed between the hydrogen and the oxygen. And so one of the ways that we keep up with valence electrons and what happens and where they go is that we use something called curved arrow notation. So curved arrow notation has some rules. You are going to use curved arrow notation for the rest of the time in organic chemistry. You need to know these rules. These are really important. In other textbooks, or when you hear people, this is also known as arrow pushing. So that's one of the things that you'll hear it called. And basically, again, we are just keeping up with valence electrons, okay? So here are the rules. A curved arrow, when we're doing a mechanism and showing curved arrow notation, represents the movement of valence electrons, not atoms. We're not showing anything to do with atoms here. Really, we're just looking at valence electrons. Sometimes valence electrons drag atoms along, but we're not showing the movement of atoms. Each double-barbed curved arrow, which looks like this, represents the movement of 2 valence electrons. If you are seeing the movement of 1 valence electron, you would just have 1 barb. That's what that would look like. A curved arrow that originates from the center of a bond represents the breaking of that bond. And then the curved arrow that points to an atom represents the formation of a new sigma bond if the electrons were originally on another atom, or the formation of a new lone pair if the electrons were originally on a bond involving that atom. So I want us to look at an example. So we're gonna see the mechanism here for the reaction we just did. Okay, we have the hydroxide ion, and it is going to react with hydrochloric acid. And what we're going to see here is that these electrons are going to come out and they're going to grab that proton, and they're going to pull that proton back to form water. Okay, this proton here is now here. So the electrons, though, are the things that are moving. The electrons go out and grab that proton and then drag that proton back. Now, the electrons don't take any when the electrons grab that proton, the proton doesn't have time to pack its bags. So it doesn't take any of its electrons with it. So these electrons that made up this bond now go and live on the chlorine. When that occurs, we now have the chlorine here surrounded by 8 valence electrons, and we know that now has an overall charge of -1. So we will continue to practice this in class and all the way through chapter 7, 8, 9, and 10. So we will definitely get a lot of practice in here. And this finishes our screencast. This is just section 6.1 because 6.2 is pretty long. So 6.2, we are going to start looking at the proton transfer reaction outcomes, as well as pKa and acid and base strengths. And like I said, 6.2 is pretty long, so I decided to go ahead and break up 6.1 and 6.2. But we will continue to practice this in class.